But then, like, if one of you needs the room, three of you are screwed.
Well, that's why there's a big open room.
Oh, okay. That's 160.
Why don't you just do bed bed, no need Tori?
I was at 8:30.
I think we should do it. It should be bed, you can walk yourself up.
Welcome back. So we're in the section talking about different continuous distributions. So how what are some examples, what are some applications, what are some of their properties like mean and variance, and we'll use moment generating functions for some things today as well. We'll start with the exponential. We've seen the exponential as an example, but we'll review it and then see some applications of it. Okay? So the exponential on a random variable. Continuous random is continuous. X, the values that it can take on are positive. Any numbers greater than 0. The probability density function, f of x, is related to a parameter, 1 over theta e to the negative x over theta in our book, where theta is some parameter greater than 0. And so in general, the density function, density function, if you graph this thing, is f of x, generally the downward sloping curve, highest at x equals 0, and then going down after that. So sometimes it's used for survival, like how long does it take until something happens, right? Things that usually are happening quickly, but occasionally have a long delay, sometimes have this model, or some of the examples in the book deal with concentrations, where there's usually a low concentration of something, but if something kind of goes haywire in the system, then there's kind of a longer distribution, and you can get some bigger values, but a lot of them are small and concentrated. Right? What's the expected value of x? As well, we're going to take the integral over the positive density of x times 1 over theta e to the negative x over theta d theta. And integrate that thing is really an integration by parts application. An integral of the e to the negative x theta can be done pretty directly, but with the extra x out here, there's a little complication. So this integration by parts, we can use our calculus. You can let you break it up into two pieces and call them u and v. There's a u and then a dv part. And we're going to rewrite this where we take the derivative of this one, so du is 1 over theta dx. And we're going to integrate this one to get v. It ends up being negative e to the negative x over theta. So I to check it in my mind. If I differentiated this one, the negative is still up here in the top two. If you differentiated this one, you would get back this one, right? Because you would get that same thing, but then you take a derivative of the exponent and you get negative 1 over theta. No, this should be theta in the top, right? Negative theta. Theta should be in there. So yeah, my little check helped there, right? So if this is u dv, we write u1 times v to the negative theta e to the negative x over theta, and that thing's evaluated at x at infinity, and then minus at 0. And you subtract off the integral from 0 to infinity. It was u dv, so now it's v du. The thetas cancel. I'll write them out so we keep track of everything. And then dx. It turns out that this first part is just 0. evaluating at, well, at 0, it's 0 times something, so it's just 0, right? At infinity, it's an infinity essentially over infinity. And that's that L'Hopital's rule where the limit of infinity over infinity is 0, right? So nice applications of things from the end of calculus 1, maybe even beginning in calculus 2, but right. So, but it's 0. So this one is left. This one has, well, the negatives go away, the thetas go away, and the integral of e to the negative x theta is theta e to the negative x over theta. I guess a third negative has to be there, right? Evaluated at 0 and infinity. At infinity, this thing is 0 as x goes towards infinity because it's 1 over. Yeah, so that's going towards 0. And then it's minus this thing evaluated at 0, or e to the 0 is 1. And then just a theta, and there's a negative 1, so negative theta, so it's just theta. So the parameter theta, written in this way, is just the average waiting time, or the average response amount, right? But to get it, you have to go through this, the calculus, to figure out what this expectation is, right? So important parts, this is the definition of expectation. The expectation of the x times the density, and then the rest is working out the calculus to figure out what it simplifies to. But any questions? Yes.
How is this different from? I have another section in my notes that I labeled exponential random variable.
Yeah. It's possible that I did another example. So instead of doing 1 over theta, some books write this as a parameter that's multiplicative, right? So the other parameterization. So let's say lambda is 1 over theta. Then the density would be written as lambda e to the negative lambda x for values of x greater than 0. And the parameter, whichever one you're looking at, they're both greater than 0. This graph, this thing has the exact same shape, right? And written like this, and the expected value is going to end up being 1 over lambda. Because it's just 1 over that, right? So half the world writes it one way, half the world writes it the other way. And whenever you're talking about this, well, what do you mean by the parameter? Is it 1 over the mean, or is it the mean? Looking back over the book, and getting ready for today, the book in that section does this version, so that's why we're looking at this. Whenever you go to a computer program that generates random numbers, generate random exponentials, or the random gammas that we're going to do later, it's good to check what do they mean. Is it 1 over, or is it just that? Yeah. So yes, this is basically the same group as before, but now with the other parameterization. Good.
So if our book were to give us a value of, if our book was to give us a rate for an exponential random variable, they would be giving us a theta?
I believe so. So in reading the problems that are later in that section,
Okay.
they talk about the mean is such and such.
Thank you.
Yep. So doing this parameterization, right? Doing this one, then the cumulative distribution function is an integral from 0 up to x of that e to the negative. Let's put a space holder there. Ends up being 1 minus e to the negative x over theta if you work it out. Where theta is the one that is the mean. And so that ends up being the cumulative distribution function. That, it slopes up pretty fast and then asymptotes at 1. Because a lot of the probability happens right away. And then there's a long tail that goes out there. The probability that x is greater than or equal to some point is 1 minus the probability that it's less than that. So it's 1 minus the density, or the CDF, sorry. And so that's just e to the negative x over theta. If you go through integration by parts twice, you can get that doing it once, the expectation is just theta. The expectation of x squared ends up being 2 times theta squared. So then the variance of x in this exponential, since it's the expectation of x squared minus the mean quantity squared, it's 2 theta squared minus theta squared, just into the theta squared, and the square root of that is our standard deviation. So for this exponential, the mean and the standard deviation are both this parameter, theta. All right, so let's look at one. We're not going to go through that calculus, because you have to do the integration by parts twice, and then it works out to reduce x squared to x and get rid of x, and then integral. So problem 5.53 says that there's a large city, and they're looking at the quantum measurements of hourly carbon monoxide at monitors in the city. And it says that the distribution is roughly exponential with mean 3.6 parts per million. So the book phrases at the mean as 3.6 because theta is the mean, and we're taking theta equals 3.6 in the model. Right? The amount of parts per million is this downward sloping curve. We can ask the question, what's the probability that x is greater than 9 parts per million during an hourly measurement? Well, from the formulas, you can do 9 to infinity, 1 over theta, e to the negative x over theta dx. We also know that works out just to e to the negative x, 9 in this case, over 3.6 as that. And so that works out to be about 8%. About 8% of the time, the measurement's over 9 parts per million for the carbon monoxide. Because carbon monoxide is not good to breathe in, not good for plants. Right? And so if they did some traffic abatement, right, more inspections, more checks on cars, something to reduce traffic, more parking outside, more public transportation. Right, so we have traffic adjustment so that the rate of carbon monoxide then is still roughly exponential in its distribution, but with a mean of 2.5 parts per million. How are things going to change? We could ask what's the probability that x is greater than 9 parts per million. And it would be this e to the negative x over the parameter, and that ends up being about 0.027. So with the lower mean, the chance that you're bigger, much bigger than that, becomes less, and it's reduced. Any questions? Yes.
So when you're putting the bounds on the integral, it corresponds to a strict inequality in terms of.
Yeah, so if this was greater than or greater than or equal to than with a continuous one, it's not going to make a difference in the probability because there's infinitesimal area right at that point, as opposed to the continuous ones which had probability at different places. So let's look at another density. This is kind of related, right? So we're going to have two variables, x and y, and we're going to have the joint density of x and y is 1 over theta squared, e to the negative y over theta where 0 is less than or equal to x less than y less than infinity, or less than. So it's going to be the joint density for both x and y. You know, maybe it looks a little funny that x isn't in there. X is kind of implicitly in there because there's a restriction on the range over here. So this thing is going to be 0 otherwise. So I've got a plot of just the xy plane, and here is this. So y is bigger than x. So the density only exists on this little upper triangle area. That's the only things that are allowed. So x is kind of a first time that something happens, and y is going to be a second time that something happens. So that's the joint density, dealing with two variables at once. What is the marginal distribution of x? What does the density of x look like? Well, to find that, the density of x, we're going to integrate the joint density of x and y over a space and get rid of y. Now, we can't just generate, y goes from 0 to infinity. It could be any number. But given a value of x, y can't go below that. Right? Y is stuck between x and infinity. So actually, we're going to integrate this thing from x to infinity to cover all the places where the density is positive. So for a given value of x, right, we want to get the density here. So we're going to integrate from y going from that point all the way up. Try and find out what it is. And this density, so we're integrating x to infinity. It's 1 over theta squared e to negative y over theta dy. And so we'll get a 1 over theta squared, e to negative y over theta gets repeated, and then there'll be a negative theta in here. And that's evaluated at x and infinity. So y is at those values. And at the top one, when y is infinity, when y is going off to infinity, right, that's going towards 0 because of the negative exponent. So that one's becoming like 0. And then there's a minus, but there's another minus there. One of those thetas cancels. Right? And we put x into there. So what does x turn out to be? Kind of marginally, what's the distribution of x? So we have that density function, and x can go, if there's no restriction based on y, if y is not there, x can go over the whole real line. And so then x by itself is exponential with this parameter theta. So. What is the distribution of x given y? What is the distribution of x given y? We didn't do too much of this with things, but conditional probability, conditional densities were just like conditional probability. So this is the density of x and y together over, I guess we need the marginal density of y. To do that, what is that going to be hard to x given y? Yeah, I do want to do that, but we need the density of y first. Well, that's going to be an integral of our joint density. That was that one. Yes, okay. But now we have to get rid of x. We had this restriction that if we have a value of y, x can't be bigger. X is kind of a first measurement, and y is a second measurement in time. And so our range of x that we, given this y that we're interested in for the value of y, we only can integrate x in a certain range. Turns out. Okay. So what does this end up being as an integral? There's the 1 over theta squared. There's a negative theta up here. Negative y over theta. And then x could be 0 up to y. Did I do something?
Did you say that was 1 over theta?
So right. No, I'm sorry, I'm making things wrong. This is 1 over theta squared, and this is y over theta. But I'm integrating with respect to x, so I don't need to do anything. It's not fancy at all. There's just an x, because there's no x here. It's just like a constant. It's like a number. Even though that y is written there, it's just x. So there's, just add that. And then x can go from 0 up to y. The density of y then ends up being 1 over theta squared y e to the negative y over theta. Right? This is actually going to be something we'll study towards the end. That's the density function. It's not one we recognize yet, but y is what's called a gamma random variable with the parameter 2 here, and then our parameter 1 over theta. Y is, we'll see later, is really kind of like the sum of two exponentials becomes its gamma. So the point of doing this one in this one problem here, we were looking at trying to get at what's the conditional distribution of x, given that we have our second measurement at y. So we take that ratio, maybe I'll write it on the next page, f of x given y is the joint density. And now we figured out the marginal for y. F of xy is 1 over theta squared e to the negative y over theta. And in the denominator here, it was 1 over theta squared. There's an extra y term. And negative y over theta. And then this thing ends up just being 1 over y as a density. But what are the limits? How can x go from 0 to infinity, or is there some other limit? Well, we had this restriction that x in this density was less than y. And so if we are given a value of y, saying we're going to measure two things coming along here, and we know that the total is a certain distance, what was the distribution? How big was the first one? Well, with these densities, it ends up that, right, what does that density look like? Here's x. Here's the density of x given y. Well, it just says it's 1 over y, whatever that is. And it can go from 0 up to y. So that's just a flat line as far as x is concerned. So it looks like x given y is a uniform random variable on 0 up to whatever the value of y is, using these densities. And so, in part, this is just an exercise working through some of these integrals. Yes?
Yeah, I think I missed the part where you told us like what this is for. Like, like you're saying distributions and whatever, but
Yep.
like,
So,
context.
right, so the context, right? So in one part, you're just working with mechanics. If we're given this joint density of x and y together, if someone were to ask what's the marginal distribution of x, you would integrate out y and get that one. If you wanted the marginal distribution of y, you would integrate x and get that one. If you wanted the conditional density, well, you would take a ratio of some of these different things. Right? The application where this type of thing has is you have some time zero starting here. And if you go until the first thing happens, right, so the first occurrence of something happens. And if that has an exponential 1 over theta distribution, then it would have that probability density of x. Right? Now, if you start from there and wait till the second one comes, maybe it'll go, a little bit longer. This is where the second occurrence occurs of something. So you wait for the first bus to come, and then you're waiting for the second bus to come, or you're taking a measurement on, some amount of concentrate. Well, I don't know, that's harder to get in that, but it's kind of this waiting time until the first event, and then the second one happens. Right? And so if there's x1, which is the first one, and that's, we'll just call it x, and then maybe x1, and then x2 as the second one, y is going to be the sum of these two time periods. And it turns out that if you add together two exponentials, we're going to get something called a gamma random variable that we will talk about shortly. So if x1 and x2 are both exponential random variables, and we add them together, we get that density that we had. We haven't done the methods of really getting at what that density is. We will shortly, after we do these things with these variables, we're going to look at transformations. How do you go about knowing that if you added two exponentials together, you would get that one, getting the gamma. So just another application that's building towards more understanding what is this gamma random variable. We're going to have another formula for that as a kind of a generalization of the exponential. Yeah.
So I'm keeping all my Greek letters straight. In the beta distribution, we talked about like the funny T-looking thing. What was that?
So in a beta distribution, so I usually do, the beta distribution had parameters and had kind of a gamma of alpha and a gamma of beta thing in that.
So is the gamma we're talking about now a different gamma than that gamma?
This function is going to show up in it, but there's a gamma random variable. So the gamma is just a numerical function, and we'll kind of try to tie these two things together today. So good. Thank you for the questions. We'll continue to look at this, right? So those are those things, right? So the exponential. Just give you one exponential, you can calculate probabilities. We've looked at the mean variance. Right? Another way we describe these distributions is moment generating functions. And this is in 5.10 of the book. The general definition of what a moment generating function is. The moment generating function for a random variable is the expectation of e to the t x. And if you take the first derivative of the moment generating function and then set t equal to 0, the first moment gets reduced and you get the mean. If you take the second derivative, right, and then set t equal to 0, you get the second moment, and so on, just like we did with discrete. So now the question is, what is the moment generating function for exponential? So let's say x is equal to exponential. What is the moment generating function? Well, we can take this function e to the tx times the density. So 1 over theta to negative x over theta. And integrate that from 0 to infinity dx. So if we work out what that integral equals, give us this moment generating function. So theta we can pull out. And then this has e to the x, and this has e to the x in it. So we can combine those terms. So there's e to the x, and then there would be, I guess even minus x. We have the minus there. So that first one has a 1 over theta. And then this thing would be a minus t if we put it in here. It's just the minus minus together gives us that tx over there, tx. So that 1 minus, 1 over theta minus t, right, can be, if you put both of them over the common denominator, it's 1 minus t theta. So that thing can be in there. The integral of this thing, you're going to get the multiplier out front. I guess you need a negative. Right, so this is 1 minus t theta. We need 1 over that thing, right? So there's 1 minus t theta. And there's a negative because of that negative there. But then there's negative x, and you get the 1 minus t theta over theta there. And we evaluate that whole thing at x at infinity, and then minus at that other part, right? So it turns out, right, at infinity, because of the negative over here, the 1 over infinity is again like 0. That one's going away. Minus, well, there's another minus, so there's plus. The thetas cancel. There's 1 over 1 plus t theta, 1 minus t theta. And when x is 0, that one goes away. So it turns out that this moment generating function simplifies to just 1 minus t theta to the negative 1. And that's the moment generating function. So we can use this, right, to check what the mean is or other moments, right? So we can differentiate this thing. So we're differentiating the 1 minus theta t to the negative 1. So we get a negative 1 minus theta t to the negative 2. And then a chain rule, there's a negative theta in there. And that's this first derivative. So if you set t equals 0, in that, we're just left with 0, that's just 1. That doesn't impact things. Then minus minus, you get rid of those, and you're back to theta. And that was the expectation value of x. And so the moments could be used. If we took a second derivative, we get a second moment, and so on. And keep going. What happens if you scale an exponential? So, if our carbon monoxide budget was parts per million, you change it to parts per billion, right? It's like multiplying it by 1,000, right? Or waiting time could be in minutes, you could make it into hours or seconds, right? So you could scale things. What happens when you scale an exponential? So, if you have a random variable and you add something to it and multiply it by that, the moment generating function for the new variable is calculated as e to the at times the moment generating function of x at bt, like a scale. So for instance, if you set A equals 0, just to scale it, like going between minutes and seconds or to hours, changing that scale. So let's say we change 60 times x. And this might be going from minutes, from hours, and hours that it takes things to happen. And y is now going to be in minutes. What's the distribution of y? Well, we can figure it out by finding the moment generating function. And if the moment generating function looks like something we recognize, and the range of the values is appropriate, then it has that probability distribution. So what's the moment generating function of y in this case? Well, if x were exponential with some parameter theta, a in this case is 0 and b is 60. Right, so the first part just goes away, it's nothing there. But this would say to take the moment generating function of x, but now if this is 60, right, so we do 60 times t. The moment generating function of x was this 1 minus theta t. So as a function of t, we, whatever t was, we plug it in there. And this time we're taking 60 times t. So we're going to plug 60 times t into that thing. And it ends up being 1 minus theta times 60 times t. Right? That's how the moment generating function changes. So if you're plugging 60t into that, where you had t before, now you have 60t. So what does this thing look like? Think about putting those things together. It's still exponential. It's still the exponential moment generating function. So the answer then of what is the distribution of y is that y is still exponential. And its rate is 60 times theta. Instead of just being theta. Yes?
Did you just know that because like multiplying by 60 would like make it grow really fast?
So in the function, this moment generating function for the x variable with t and this 1 minus theta t to the negative 1. So we put anything in here, whatever is going to be in here is going to show up in the place of t. So if we multiply it by 60, 60 times x, then the moment generating function of y is going to be the moment generating function of x with 60t plugged into there. And so it's, this spot here, I'm just going to have my 60t. So if I multiply it also by 24 if it was in hours, I need to multiply it by 24 to get it to, if it was in days, I multiply it by 24 to get it back to hours, and then 60 to get it to minutes, and whatever that big multiplier is would just show up here. And my new parameter is there, and y still has that exponential form. So the CDF, the means, the standard deviations, all those relationships still follow the exponential with this new parameter, which is convenient, right? That is still that, right? There's a lot of continuous distributions that exist on the positive real line, and if you did something, there's no guarantee that it's going to stay in the same family and still be exponential, but it does in this case, and so that's convenient for doing that, calculating things. Right? Any questions? So we're going to look at a variation. In this, we're going to look at the gamma random variable. In 5.5, right after the exponential. So if x is a gamma random variable, x is a random variable that has a gamma distribution, it has two parameters, usually called alpha and beta. The gamma distributions are positive random variables. The densities that you have for this can be exponential. Exponential is a special case, but it also can start out with probability that really kind of starts accumulating away from zero. So the gammas can go up like this and kind of then go out like this, or they can go a little further out and go out. They also can be exponentials a special case, so they could just slope down. So you imagine something that's positive, occurrences of things, modeling of other chemicals in the air, nitrogen or helium or something in the air, or ammonia and different chemical reactions. And maybe it's not reasonable for it to all be so heavily towards zero. Maybe in the things that you're studying, there's always a little presence of something there, and it's a little further away, right? So this big concentration at nearly zero might be unrealistic. But, but these other flexible things. The density for this thing, probability density function, is 1 over gamma of alpha. There's that gamma function. Beta to the alpha. Right? X to the alpha minus 1, e to the negative x over beta. And if we have alpha equals 1, then that density becomes just 1 over beta e to the negative x over beta. Right? So it's an exponential beta as a special case. But that alpha in there can modify the shape and cause it to be out further. Right, so that's going to change the mean, change the relationship to the variance, change the moment generating function, and other things. Right? So what is this gamma function? The gamma of alpha. The gamma of alpha is a function, a mathematical function. It defines an integral from 0 to infinity of x to the alpha minus 1 e to the negative x dx. That's what the gamma is defined. So it's for every value of alpha, it's a number. Right? There's actually functions in R and probably in a lot of other computer programs like Maple or something to compute this. And so, our studio going for a minute here. There's a function for calculating gamma that you can put in. That'll get going in a minute. There's a relationship that you can show with integration by parts that the gamma alpha plus 1 is alpha times gamma of alpha. That if you have gamma alpha plus 1 and then do integration by parts, you can reduce the exponent by 1 and produce the next term in the sequence, and there's an extra alpha in there. So it kind of goes down. And we talked about with the betas that if alpha is an integer, that the gamma of alpha plus 1 ends up just being alpha factorial. So it's kind of a combinatoric type thing. It doesn't show up quite as much in this one. It's more of a constant to make sure that this thing integrates to 1. Right. Let's see if this RStudio has started yet. So in RStudio, there's help of gamma. There's special functions of mathematics. There's something called a beta function. Here's the gamma function. Right. Gamma of x, so gamma of 6 is 120. That's factorial is another function. Right. Factorial of 5 factorial is 120. So, but these things get used in enough applied mathematics, computational problems that there's special functions that are programmed and computed. Right? I think calculating this integral is really by quadrature, so it's not a closed form expression. Instead, they have to do numerical approximations to get this thing as accurate as possible. But it's programmed in. Gamma, like the factorials, grows very fast, so a lot of times it's evaluated on a log scale. And then that's, you know, if you're taking the differences between gamma functions or ratios, they often do it computationally in terms of log because these things grow so much. So anyway, the functions, these special mathematical functions are in there. There's also things in R then for the distributions. Right? So those are the density for a gamma, or the probability that cumulative, the CDF function, or finding quantiles, percentiles of a gamma, or giving random values of the gamma. And there's a similar thing for exponentials. Distributions in R, you get the density or the percentile, you know, the cumulative probabilities, or the quantiles or random variables. One thing to check in whenever you're using a computer program like this. Now, here it says we're going to get a, you know, there's a rate factor in it, right? So there's a parameter. That's the, is that theta or is that 1 over theta? Is it the mean or is it 1 over the mean for application? How would you want to check that? Well, one thing we could do is take, we could generate 10,000 values from 1 and say the mean of, put 3 in there, right? So this is going to rate equal to 3. If that average is 3, then it's theta like we've done because we theoretically had the average of 3. If it's 1/3, then it's 1 over that. So it turns out that here they're doing 1 over. So if I wanted to generate exponentials with a mean of 3 in R, you got to switch to the other parameterization. The standard deviation should also be about 3. Similar thing would happen with gamma. There's a rate, or if you want to call it, give it the name, the scale, 1 over it, you can just go directly to that. But anyway, it's always an issue. Which parameterization are you dealing with, no matter whether you're in R or another program or a journal article or something. Right? So that's what this gamma function is. That figures into there. You can show that the integral from 0 to infinity of that density equals 1. The key thing is that that gamma function is really defined in a way so that x to the alpha minus 1 e to the negative x. That thing integrates this, and it's here in the denominator. The betas are essentially just a scale change, like a multiplier that you could use change of variables to get rid of those. But it integrates to 1, right? What is the, then we could also look at the expectation of x. What is the average value for a gamma when it has these 2 parameters? So you're going to have to do integral of this, gamma of alpha. There's a beta of the alpha down here. X to the alpha minus 1, e to the negative x over beta dx. Looks a little bit messy, but we handle this one much like we did with the beta distribution. We're going to kind of match a pattern, right? Let's pull things out that can come out. 1 over gamma alpha, beta to the alpha, and then combine some terms. X, I'm not going to make it just alpha. I'm going to write alpha plus 1 minus 1, and e to the negative x over beta dx. And so I think it's pretty clear to see that that kind of looks like a gamma distribution to some degree. It's kind of the gamma part involving x. It's what I would call the kernel of the density, or the part that involves the variable. Right? And so it's a power minus 1 here, and x minus x over that power. But what we don't have written right there is this multiplier thing here, or I guess that multiplier is all in the basement here, so I'll probably put it 1 over c. So if we can write the proper multiplier here, that whole thing is going to integrate to 1 and be gone. put something there so that it's 1, and then have 1 over that outside. If this is the density here, and that all integrates to 1, right? We need the corresponding part here. So that C, to make it work out, well, we have alpha plus 1, so we should have a gamma alpha plus 1 down there. And we have a beta, but instead of beta to the alpha, we should have alpha plus 1. So if you put that thing down in the bottom, right, then that whole interval should integrate to 1 because it's a density. And then you're left with the C out front, so alpha plus 1, beta to the alpha plus 1, and this is gamma of alpha, beta to the alpha. Right? Can you simplify that? There's obviously 1 extra beta up there.
Alpha factorial over alpha minus 1 factorial is just alpha.
Just alpha, yep. Yep, if you step this down 1 alpha times gamma of alpha, they cancel. We're thinking about factorials, it's perfectly fine. And so the mean is alpha times beta. It turns out that if you go through the expected value of the square term, you can do it kind of the same way. The variance equals alpha times beta squared for this one. So connecting back to that problem at the beginning. Right? So if x1 and x2 are independent variables, and you say y is x1 plus x2, there's a relationship with the moment generating function. The moment generating function of y of t is the moment generating function of x1 times the moment generating function of x2. If x1 is exponential beta, and x2 is exponential beta, and then we take that, and they're independent of one another. Y, x1 is the sum of those two things. Then it turns out the moment generating function of these, right, is the moment generating function. The first one, which is 1 minus theta t minus 1, and 1 minus theta t to the negative 1. So these things become 1 minus theta t to the negative 2. And it turns out for a gamma random variable, if this is alpha, and now I kind of switch between the beta, the other one was beta, but yeah, I'll write it with beta first because that's what the book does in this chapter. The moment generating function of a gamma random variable is 1 minus beta t to the minus alpha. If you know that fact, what is the distribution of y? So the sum of these two exponentials, if this is true, well, this has an analogous form to that thing. So the sum of these two independent exponentials is going to be this gamma random variable. And it's going to have a parameter of 2 here. And then I've called it theta, corresponding to what's done there. So it's going to have that. So its mean is 2 times theta. Its variance is 2 theta squared. You could use the R functions for gamma to calculate probabilities, that if you had to wait for 2 successive things to happen, how long would it take for different events? What would be the probabilities? so it can model other circumstances. So let's return to it. So anyway, this was some of the connection to that initial problem, thinking about a first waiting time and then a second waiting time. If they're both exponential, then the sum is gamma. And one way to see that is through these through these moment generating functions. Yes?
Can you just scroll up a little bit, please?
Yeah.
Thank you.
Moment generating functions, we have two independent things added together, they're moment generating functions. The sum is the product of those. Right. So let's return to an example. So you're in the large city. And now let's say that the the hourly measurement of carbon monoxide doesn't follow an exponential distribution, but it follows a gamma distribution with parameters 1/2 and 7.2. What's the expected value of carbon monoxide? Average, this is parts X parts per million. So average parts per million, well, it's alpha times beta is the product of those two things. 7.2, 3.6 parts per million. 3.6 is what we used for the exponential in the previous one. Yes?
What does alpha and beta mean for this application? Like, because we originally said, I think that 7.2 parts per million was the CO2 or the carbon.
We said, I think
dioxide.
3.6 maybe was the average.
Yeah, so what is the 1/2 and 7.2?
So with the other one, we had exponential, 3.6. That would be like a gamma random variable with a parameter of 1 and 3.6, because the special case of the gamma is that. Now I said that no, it's not exactly that. That there's a little bit different shape to the distribution. Instead of curving down exactly like an exponential, it's a little modified. How would you know that? You had enough measurements over time and plotted the histograms and tried to match it to a density curve, maybe that the other one would fit a little bit better. A little more flexible. Right? This one says that the expectation, this one, the exponential, says that the average is 3.6 parts per million. And this one says that the standard deviation is also 3.6 parts per million. So it's fine as a probability distribution, but it's a little restrictive in terms of that relationship. The gamma gives the average as this. The variance is alpha beta squared. So 1/2 times 7.2 squared. Which happens to be 25.92. The standard deviation in parts per million is the square root of that. So the square root of the 25.92 is going to be 5.09 parts per million. So this particular gamma has the same average as the other one, but a little more variability. Yeah.
Well, I guess just, and also, like, how is alpha and beta used within the context? Like, is it increasing from 1/2 to 7.2, or, like?
So
why
these would
do
be two separate values, right? So if this is our value of alpha, and this is a value of beta, the probability density function has alpha and beta in there, right? So the density for this function, one's gamma of alpha, beta to the alpha, x to the alpha minus 1, d to the negative beta. And so if alpha is 1/2 and beta is 7.2, then to find the densities, you're going to plug in those values for any value of x and see what it looks like. We can graph some of these densities as they're changing. So the alpha and beta change the shape, and then they change the likely values of x. And as we mentioned here, this particular combination, 1/2, 7.2, gives a higher standard deviation. So that would allow more extreme values. So on some days, if it really gets bad in terms of the pollution, right, maybe this gamma model would better fit that, and you could calculate the chances of getting extremes. Right? So, get this up here to see it. So, let's see. Let's double check what's going on with the gamma. Let's get 10,000 values of gamma. Let's put the first parameter as 1/2, the second as 7.2. Are we going to get an average of 3.6? No, we don't. It's called the scale parameter. If we do that, okay, that's fine. You can either do it scale or rate. You could do 1/, that parameter just like 1/. So if it's done this way, then it's R1/2 and R7.2. And if you generate a bunch of those and take the standard deviation, it's about the 5.2 that we wanted. Let's generate a bunch of take probabilities that go from 0.01 up to 0.99. So this P is just all these different percentiles. And we can do quantiles for a particular gamma distribution by using this Q gamma function. So I'm going to put my 1/2 here and my scale equals 7.2. Right? And so those values, well, they start out very small and they're going to get bigger, are the corresponding percentiles. Right? So the 99th percentile, if you multiply this by 10, is 23. 98th percentile is 19.5. The first percentile and the second percentile, they're all very small positive numbers. Right? And so most of the values you're going to see in terms of this are going to be kind of in that range, with a lot of them kind of in the middle here. So I think if I round this to kind of something about 3 decimal places, maybe I'll do it 2 decimal places, you get, it's not exactly 0, it's a little bit positive. But so that is kind of describing all the different percentiles there. So if we did a histogram, say, let's do a histogram of, say, 10,000, I don't need to do any round it, values, this random gamma, a lot of the values are pretty small. We had an average of 3.2, so the average is back here. But there's a few points out here that are pretty big. You could have some days with this really high carbon monoxide. The contrast that has the same average, right, is this exponential, right, with rate, is it also called scale, 3.6? I didn't like scale. We're just going to give it 1/3.6 to make it work out to the same mean. And so that's the graph. It looks very similar. This is a small change going from this between these two. Not drastic, but these high values out of 10,000 cases are 20, 25. This other one had some up at 30, 35, maybe even 40. Right? The change to that gamma allowed those extra values to be plausible within the distribution. You said, oh no, it's only exponential, and then you got some other the points up there, 30, 40. It would seem not very consistent with that exponential. It doesn't have enough variability. The switch to the gamma has more variability. Anyway, if you push this, we could calculate the probabilities we had before. What's the probability that we're greater than 9? So in this one, what's the probability that we're going to get a measurement over 9? For the gamma, we don't have a real closed form solution. The exponential is real simple with that one parameter, and we got a value there. But if you put this into the computer, 1 minus the probability that x is less than or equal to 9. The computer will tell you that it's 0.8862, so the probability is about 11%. 11.4% over 9 parts per million. In contrast, when we did the exponential 3.6, which is a gamma with 1 and 3.6, that particular one, then the probability that x was greater than 9 was less. What was that in the example? It wasn't as likely for one number. And further. Oh, it's right in front of us. It is about 80%. So about 8.2% over 9 parts per million. We could look at one more extreme, right? So yeah, the exponential had less variability in the tails. This particular gamma had more. What if alpha is 1/4 and then beta is 14.4? Right, the expectation is still alpha, beta, is still set at the same thing. The standard deviation, I think, is going to be more. And the probability bigger than 9 is going to be even more likely. It's just how these two parameters are influencing things. So let's take a look. So in R, right, there's this P gamma. It's a cumulative probability of gamma. So if you put a 9, and then our parameters, the exponential, called a scale, 3.6. Right. And 1 minus that is the probability you're above 9. So it's about 8%. But if instead the parameters were changed, right, to put a little more variability, the probability is going up. If instead it was this 1/4 and then doubled that, 14.4, the probability would go up a little bit more. Those, as the alpha and beta change, you can change the mean, you can adjust the variance, and that's going to influence the probabilities that it's concentrated towards 0 or that it's above a big value, and so it could fit different data situations. So those are our distributions and things for today, really, right? So we've had this exponential random variable, which we generally call it beta, as a special case. As a special case of a gamma random variable. We've had a general case of a gamma random variable. The expectation here was, make a little chart, expectation. This is beta, this is alpha times beta. Variance, beta squared. This one's alpha times beta squared. And we looked at probability densities, some moment generating functions. What were the moment generating functions for these things? There was 1 minus beta t to the -1, and this one was 1 minus beta t to the negative alpha. And there was a few things that we could do with those. Right? Any questions about these? So on Thursday, we'll look at normal distribution and some other variations on symmetric continuous distributions. And I believe that mostly will be what we'll do in terms of introducing different variations and continuous distributions at this point. We'll move on to some other applications in probability and maybe see some others along the way. All right, stop there.
A little bit early.
There's a homework, wait, I'm thinking homework 6.
Yeah.
That's on Thursday. Thursday, yeah.
Thank you. Did you get any stalls?
Which is why I think it's tricky, because then we focus on the book for delivered spells and then we weren't there.
Have a good one.
Like the ninth. That's where it was like the cycles were lost. And you have like the dependency.
I know, I drew it out, how they would line up, but I don't remember how many lost cycles I got.
I got a lot.
I have no idea. Yeah, I know, I drew them both out, but. I remember.
See you.
See you, Jake.
Thank you.
See you. Yeah, between the two classes, I think that they do the exponential differently.
Yeah, yeah.
So,
definitely.
it's kind of a-
I'm getting used to it though, just seeing, recognizing the same stuff.
Yeah, it's gonna be one way or the other,
Yeah,
so.
I think going through the homeworks, I'm probably definitely gonna mislabel it a couple times.
Yeah, just, you know,
But-
watch what's in the book for that one.
Yeah.
So, in any case.
But I'm getting used to it. Thanks.
Yep.